Now we're going to talk about the sampling, and the sampling is uh, really broken into two parts. The one is to get samples to measure PVT data, to tune the equation of state. And why do we need a good equation of state? Because all of the calculations in gas condensate, the flow in the reservoir, have strong PVT dependencies, viscosities, volumetric, and then you've got even flow through the pipe at varying pressure and temperature. You need to have a PVT model for that. And certainly this maximizing the liquid recovery at the surface, you need some kind of model to tune the surface processing. So you need an equation of state for many reasons. So you'd like to develop an equation of state based on quality data. And that's the one reason that you collect samples and measure PVT data. The other reason to do sampling is to identify the composition or the solution CGR spatially and how it varies spatially. That's basically to know like permeability, porosity, saturation, anything else. You know, what is the spatial variation of the fluid in this case? So we therefore define samples as being either reservoir representative or in situ representative. And reservoir representative means that whatever sample you collect came from the reservoir fluids, okay? Even if you collected samples after you'd gone below the dew point and you still collected samples and you tuned the equation of state to those samples, that equation of state should be able to predict properties of what was originally in the reservoir had you known that composition. So you basically, the only requirement for reservoir representative samples is that you don't have some kind of like oil-based mud contamination in those samples, not representing the reservoir fluid itself. The other is that, well, this basically that defines reservoir representative samples. So it's basically no or little oil-based mud contamination. That's the target. And then you want the laboratory to make good PVT measurements of those data, of those samples. So those become very useful for EOS model building. Or just QCing an existing EOS if the PVT data is good. Okay. Now, in situ representative samples are samples that actually represent a point-specific or an interval-specific average of the compositions that are in situ in the reservoir. There you're trying to use those to map out the spatial variation. Here you only really need compositions. For the initialization. You build the EOS based on reservoir representative samples, and then you find out what the compositions are and put those into your model. The equation of state should be able to accurately predict PVT properties for any of those compositions found in the model. Now, if you have samples that are in situ representative with good PVT data, you can obviously include those in tuning the equation of state. But for the mapping part, we only need real compositions, but if possible, it'd also be nice to have saturation pressures for those samples so that you kind of can map how far are you undersaturated or not for given samples. Basically, you like to map the saturation pressure of the sample spatially as well. Okay. Now there's a section here on sampling that we probably won't get to until tomorrow. That's dedicated to what types of samples there are, when to use them, how to use them, and so forth. Any questions about sampling or these two types of samples?
I have a question. If we have a saturated reservoir and the reservoir is, we have a neighboring reservoir which is interfering with this reservoir. So at the time of the sampling, we are not at the initial reservoir pressure. And so we have some condensation before production startup. And if we assume that we get a representative sample at so that condition, that situation, how can we reproduce the original fluid composition at the initial pressure, or what trick we can do to somehow represent that in our PVT?
So let's turn the question a little bit around, okay? Let's say that we had a sample that was truly in situ representative, okay? And what we did is that we whatever. So let's say that our original dew point is here. Okay, and let's say that we have liquid dropout from this correct sample. Okay, so that might be the liquid dropout. And then I'll put the gas composition. It looks something like this. Okay, so this is Y C6 plus. Okay, so we've got this behavior here, and we've got this behavior. Now, what we're going to do is that we tell the lab, we only want you to give us data starting here. Okay. So they're going to give you this composition of gas, right? That's the sample you're saying you went out and collected. Okay. So what you're wondering is how to reconstruct this composition, right? Is that? Do you see what we're doing? Yeah. Okay. Yeah.
Yeah, exactly.
So
yeah, exactly. So that's what I want.
If this is your actual sample, then what you want to do is first just tune it to the equation of state. Okay. Then you calculate obviously the dew point, which is equal to the lab data. It's matching the lab data. Now your sample that you actually have here, when you do the CCE or CVD of this test, will look something like this. Make this way. See, it's going to have a dew point here, and then it's going to have, liquid dropout that looks something like that, right? It's going to be leaner. But this is the data that we actually are going to be fitting with the US to these data. And then you calculate the dew point, and that gives you the incipient oil or condensate, right? Composition YI at P star, right? So then what we would do is that this actually is a method that Jan Refstrup in Denmark proposed in a paper. It's hard to get a hold of the paper, but basically that you just add this, I'm going to call it YI star, this XI star to this composition that you actually have, this, I'm going to call it, right? And elevate the dew point. Now you may not know what the actual composition is or the dew point should be, right? But you can do that. You can do that. I'll do this in pink. You can do that like that, okay? And you create the extension of that curve. And remember, this curve is the same as little rs curve, right? You basically create this extension out here. And then, maybe there's an initial reservoir pressure limit or not. I don't know, but it probably, since you say you went below the dew point. So you basically you create the curve that you need. And then what you're going to have to do is just make an estimate and say that, okay, well, I go to the initial reservoir pressure. We knew that. Or you go to some CGR. You have to make some assumption, but you can do sensitivity. You can do sensitivity to that initialization here, right? And if you deplete any of these, you're going to come down to this sample that you had here. That's what you're going to find. So if you initialize with any of these calculated extrapolated to get these points here, if you take any of those and you deplete, you take that one and you deplete downwards, you're actually going to get to this. You're going to get to this sample that you collected. Close, very close to it. Okay.
So you mean mathematically you combine the incipient oil with
so you extrapolate. That's right. You mathematically
gas
recombine them. You take
composition
it to the equation of state. The equation of state will calculate a new dew point, new dew point, new dew point, new dew point. That'll give you 4 new compositions with 4 dew points, 4 little rs values. You can just use whatever you want to use there. 4 sensitivities. And basically they'll all, when you deplete them down to P star, they'll all give you more or less the same composition of gas that you collected.
Okay, and when you create the black oil table for gas condensate, and if you insert pressures above the dew point in your black oil table generation, is it the procedure that it takes to create the table above the fluid dew point? Yeah. Exactly. Okay. All right. Thanks.
But if you're doing compositional simulation, you could just put those compositions in the model as sensitivities. or create black oil tables. I mean, it would just be one black oil table extension. You'd have a single black oil table. The key is that you want to create extrapolations that when you deplete it back down to P star, you get the same composition, okay? And you get the same depletion performance below that. This paper, I don't think we have it here, but it's by Jon I think it's actually referenced in the IBC paper that I don't think I asked him for a copy of it, but he sent me another paper, so. Oh, this is not working.
Just another question. So this first dropout, what I've
right.
experienced in some of the samples, it's very heavy, and even it creates anomalies in the PVT black oil PVT table. It's not monotonic. So is it really the correct composition
yeah, I mean, you
to
don't
take?
really have it. I mean, it's if this composition is the equilibrium gas currently. Of course, the problem is that there are many ways to tune the equation of state. You know, the problem is that you have to do a distribution of the heavy ends in that gas at P star, and when you create the incipient oil from the dew point calculation, depending how the C7 plus components in the gas have been treated, then you can get all sorts of different oils, not all sorts, but different oils. But yeah, I mean, it could very well be a heavier oil, so to speak. Yeah, and there's. Let me just see if I can find this first, and I'll get back to you. This may be. I think this may actually be the paper. Yeah, I think this is. Yeah. Yeah, I'll look at this evening and make sure it's the right one, the right paper, but that's. What you're saying is in fact, even in this Koof paper, which I think we have here somewhere. If you look at the it's like watching molasses pour out of a jar. It's like, okay. This is referring to your non-monotonic properties of BO and RS, the oil properties, the incipient oil properties, the retrograde condensate oil properties. You'll see it here as well. And it's very real. So you see the BO and the RS here, non-monotonic. You'll almost always see this for a leaner condensate. The leaner the condensate, the more, how should I put it? Let's say that we have 3 gas condensates, all with a dew point of 5,000 pounds, just like this, okay? They all have a dew point of 5,000 pounds. Okay, the one is like this, it's 30 barrels per million. lean condensate. Then you go to 100 barrels per million, also with a 5,000 dew point. And then you go to 200 barrels per million, also with a 5,000 dew point. Okay. What you'll find is that the incipient oil from each of those dew points for the leanest sample is going to be the heaviest incipient oil. And you'll get this non-monotonic behavior like this because the oil that drops out right at the dew point, if you took and flashed that oil, that incipient oil, to the surface, you get a 38 API or maybe a 32 API. Okay. But then as you go further down, the condensate that you're dropping out is becoming lighter. Okay. So the reason this is non-monotonic is because you've got a 32 API condensate here, you got a 30 API, you got a 45, and then kind of the rest of it's more or less, typical. So the problem, it's not a problem, it's real. It's a very real, but often you don't see the actual incipient oil because there is none. You don't, in the lab, the first liquid drop out here at 4,500 pounds, you don't take that out and analyze the composition. So you never see it from lab data, but this is always going to be the case. The leaner the condensate, the heavier that incipient oil is going to usually be in general. So yeah, it's not unexpected, and it is, I think, real. Now, Eclipse 100 won't let you run with these simulations. Eclipse 100 won't let you have non-monotonic. It's either RS or BO, I don't remember. RS. It won't let you have non-monotonic RS. Sensor doesn't care. Probably other models it doesn't care. But Eclipse 100 will not let you have it. So then you have to come up with some kind of fake oil properties.
But if you have a non-monotonic RS, then you would always have a non-monotonic BO.
Almost always. Yeah. I mean, but yeah, the RS is what it doesn't allow. So then you have to come up with some kind of fictitious BO curve to run Eclipse 100 for this. Yeah, so that's basically would be the recommended approach to getting the extrapolated curve. What you don't want to do is recombine separator gas and separator oil to elevate the dew point. That you do not want to do. And why? You can look at this paper 122, I can't remember the name of it. 28829. It also talks about this extrapolation and doing the same kind of thing. In fact, that paper references the ref strip paper. Yeah, that looks like that same paper that we that I showed you there. Here. Rest strip evaluation. I'll copy this over so you. And then I have to copy it over to this other one as well. Yeah, okay. So before we get started on talking about the sampling a little bit more, just anything that is unclear from what we have covered so far, now's the time. So there's a presentation I'm going to try to follow. I think here it's actually one of these e-notes called the GC sampling, and we can start maybe with just listing the types of samples that are available out there. Let's see here. Separator samples, open hole formation testing samples, MDT type. What we'll discuss equilibrium contact mixing. Wellhead samples are very uncommon. They can be collected for highly undersaturated systems, but both wellhead and isokinetic sampling is also, I think, available, but not used a lot. It's quite a bit more expensive than traditional separator sampling, but it's specifically for gas condensates, and so we'll at least talk briefly about that. And then bottom hole samples, which I've already mentioned yesterday, is not really recommended for gas condensates. So mainly we're talking about separator samples, open hole formation testing samples, RCI, MDT, the other brands, equilibrium contact mixing, which is a bit special if you have a saturated reservoir with both a gas cap and an oil in equilibrium. And that can be a very useful type of sampling method. And then that's pretty much it. I'll mention a little bit about the isokinetic just because it can help for leaner condensates in some cases. So
Chris, there's a quick question here.
Okay.
We can go through it. So I didn't quite catch why it's not as important to tune liquid dropout in gas condensate US. If you could just quickly go through that again.
Okay. So US tuning to either CCE and or CVD. It's not that you don't need to fit it or match it, but the idea is that this property here from CVD, this is what we actually produce and make money from. Okay, so this is our added value data, and this VRO is basically our lost condensate. Okay, and the magnitude of how much that is, because I mentioned it yesterday, no matter how much it is, if it's 20 or 25% or 15%, that oil is not going to be mobile. So it doesn't matter getting the actual volume right. And for leaner condensates, it's difficult for the lab to actually measure that oil volume because it's very small volumes accurately. So the fact that this is an immobile saturation, and so the magnitude is not important. That's the main reason. And the C7 plus, C5 plus, whatever you're calling condensate surrogate, is the added value. You want to get that right. That's equivalent to the RS, which we know is very close to the reducing oil gas ratio at the average pressure. So getting those things right is very important to the economics. Whereas getting the liquid dropout matched exactly or very closely is not important in terms of performance. Now, having said that, the two functions are inverse functions. Okay, the loss or the drop in Cn plus component in the gas composition is because the VRO is increasing. So I usually draw them on the same figure because the shape are very similar. So if we draw VRO here, and you know it goes like this, you hit the dew point, and then basically goes up like that. Of course, it depends. I'm going to plot the CVD. So this is the CVD relative oil volume is oil volume which changes with pressure divided by the dew point volume, which is a constant. So this actually reflects the actual oil volume in the cell. And this will often look kind of flattens out, something like that. Okay? And the gas composition up here, initial pressure, dew point. So this is the here, or you could translate it R, little rs. Okay, so that's going to look like this, and then this is going to go down, and then it may even go up a little bit there. So they're inverse-like functions. The one goes up and the other goes down. But the magnitude of change here is in stock tank barrels not being sold. So you care about it a lot more than the reservoir barrels or the oil saturation that you're getting right or wrong, because this equivalent to the oil saturation basically is going to be less than the critical oil saturation anyway. And so it's not mobile, so who cares what the saturation is? Okay, that's why now if this data here is questionable, let's say that this data, sometimes you often see bad laboratory data, this data drops down way low, unrealistically low. There's a bad material balance. So let's say that the data looks bad or unreliable, then you wouldn't use the data in the fitting. And then what you're left with is the liquid dropout curve. Okay? So if that data looks bad and you only have one sample, then you're obliged to fit this.
That data is better.
There it's difficult to know. That's the problem. But you have to, we have one customer, we had literally over 100 samples and none of the removed gas compositions were reliable. So we had to use the liquid dropout curve for every one of them. So in developing the equation of state.
There is a question about if you can give a reference for this phenomenon.
phenomena, or
Like about what, I guess it's about if you can give a reference of what you're, I don't know, what you're talking about. You think is the question. If there's a reference about uh, s- the CBD behavior, I think the experimental. Okay.
I guess there's
If you can clarify the question, also maybe.
yeah, I don't know that specific. You know, we've been presenting this as a strategy, recommended strategy for EOS modeling, use of lab data for gas condensates since the early 1990s. That there's a specific paper, I think there's a presentation, but I don't know if it's connected with the paper. Let me just see real quick if I can find it. This one here. Yeah, this was a ATW, so there wasn't a paper associated with it, but this was kind of specific for gas condensates. That's not a paper though. Yeah, I don't know what I would say. Yeah, I mean,
That sounds really perfect.
okay. So on the sampling of those that we had listed, basically we have open hole formation testing samples. And this references as SEP. And then we've got, what else was there on our list? Equilibrium contact mixing. That's probably the one that you've never heard about. ECM. And that's for mainly for saturated gas condensate with oil zone. These are the three main, call it sampling methods that we have. And then this, what's really a kind of a footnote to separator testing is this isokinetic version of separator sampling. It's usually for leaner condensates at very high rates. So maybe more than 30 million standard cubic feet per day. Maybe it's less than that, but it gets worse the higher the rate and the leaner the condensate. It's dealing with the problem of liquid carryover in the separator gas stream. Okay. All right, so let's go to the kind of the list of what's it. Wait, yeah. Maybe I changed the directory. one more time. Okay, it's all right. So fluid samples from gas condensate wells are needed for two main reasons. This we discussed yesterday. The first is to provide PVT data for developing a fluid model, such as an equation of state, and generating Blackwell PVT tables that we've already discussed. And that's what we refer to as reservoir representative samples. Basically not contaminated samples with good quality PVT measurements. Second is to provide compositional data to define the fluids in place, especially surface condensate volume, that is little rs initially, and how that maps spatially with depth and otherwise, by zone, aerial variations, whatever it might be. Separator samples should almost always be the primary source of samples for gas condensate reservoirs. That's a general rule. I mean, but if you have new discoveries or the first 1 to 5 wells in a high permeability type reservoir, because of the rig time for doing production testing, companies now will often not do production testing because they get cores, they can get open hole formation testing samples, even contaminated, for a lot less. They save all the money of the production test period, and they know the well's productivity is high, so they don't need to run production tests for that reason. But eventually you'll start getting separator samples from wells. If you don't, then you have to use these open hole formation testing samples. They can be used without really any complication if you're using water-based muds, because then you can take the samples, make the measurement of PVT data, tune your equation of state, just as if it was separator samples. We'll come back to the oil-based mud situation. Ideally, point 4, samples should be taken while the bottom flowing pressure is above the dew point, but this may not be possible in saturated or near saturated low permeability reservoirs that require substantial drawdown to get the production test. So why is this the case? The reason is because let's see, point 4, why do we want PWF to be greater than P dew point during sampling? That's pretty clear. Because the producing oil, CGR, can vary with basically with drawdown below the dew point. In a testing period, it may be that you're creating this steady state region 1 during the testing. So while you're building this mobile oil saturation in the near well region, and even if you've already built it, the producing oil gas ratio will be approximately equal to the solution oil gas ratio at P star. Okay, and this very well could be less than the initial RS. So I have a nice set of calculations that the colleague Sissel Martinson made some years back, specifically for this KUF type fluid system, showing the impact of rate dependence or drawdown dependence on the producing CGR from well modeling, detailed modeling. I think we use compositional modeling of a well test. I thought I'd show that here. At least you can look at it in more detail, but this sampling issues in CUF-like gas condensate reservoirs, studying the variation of CGR during short-term sampling for a wide range of KH products. The KH is varied because that affects the drawdown, and the drawdown affects what the P star will be, and so forth. Relative permeability effects, layering effects, and the rate sequence being increasing or decreasing. So this is an example. We take the K2, K3 fluid. That's the one with a little bit higher H2S content. Running rates from 20 to 200 million standard cubic per day. We're testing full pressure buildup between rates. And these are initial pressures close to the dew or equal to the dew point. Sensitivities, relative permeability, layering, multi-rate test, degree of undersaturation. So this is a main result from this. So if you have basically low KH, that means you have larger drawdown. And you see a much more significant variation during the testing of CGR. It's going from 26.5 to just short of 30. It should be around 31. And this is for a high KH well, where there's much lower drawdown, even though the rates are much higher. Okay. Now, why that is has to do with this this three range, or the region 1, region 2, P star is defined as the dew point of the well stream mixture equals the pressure at the boundary between region 1 and 2, and the P stars is strongly coupled with the flowing bottom hole pressure, as you might imagine. So basically, as you draw this further and further down, the P star will be dragged further down as well. And this just shows for the two extreme cases, the 5,000 and the 25,000, what the pressure looks like. Okay, and this is basically, we can identify this this radius here because we just look at the dew point of the producing mixture at a given time. That gives us the P star. We go into the model and see where does the P star exist. You were asking about the distance. These are just for short-term testing in the range of 1 to 5 feet. So the higher the P star, remember the solution, the producing OGR will always be equal to the solution OGR at P star. So the higher the P star, the higher the producing oil gas ratio.
Sorry, I have a question here.
Okay.
Well, the case was 5,000. Yeah, 5,000 milliliters.
Right.
Which composition are you taking and referring to the dew point? Because the pressure is changing.
So this is a snapshot in time. So I don't exactly know what time it is, but it's during the test. So you just take at any time step from the model or in the real well, you just take the producing well stream. Okay.
The specific bottom hole pressure, you go, okay.
Well, yeah, I mean, this is just a snapshot in time. So at a given point in time, you know the flowing bottom hole pressure, you know the well stream composition, so you know its dew point. So then you know P star.
Okay.
And because we're doing modeling, we can go into the model and say, where does that P star show up? And we can find the radius.
Yes.
So what you see here is that over a longer period of time, the CGR stabilizes, and it does so more rapidly with the larger drawdown. Here you can see that becoming, but basically they're all stabilizing within about 2 days. These are all being produced, all three being produced at the same rate. Does anybody have an idea why it might be taking longer? Because what's happening is once you build up the region 1 into a stabilized region, that CGR is going to remain more or less constant over shorter times. So that period of transient is the buildup of the kind of steady state region 1. Well, in all of the cases, you have the same flow rate, so you have the same mass rate going through this near well region, right? But where you have very low drawdown, the amount of liquid, the drops of liquid condensing out, building up that saturation is much smaller because you're okay, because you're at a higher pressure, okay? At a higher pressure, you're getting fewer drops of liquid condensing out for every minute of production. Whereas here you've got a larger drawdown, so you're getting more condensate dropping out per minute with the larger drawdowns. You're getting more condensation, so that saturation, stabilized saturation in region 1 builds up much more quickly, and that leads to this flattening out more quickly and remaining so. And by the way, this is also the same kind of thing that you see for MD open hole formation testing as well. But there it builds up even more rapidly. You can draw down below the dew point, but because it's spherical flow, the volume it needs to, the region 1 is more like a sphere instead of a cylinder. So it takes less time to reach this kind of stabilized CGR. Okay, so this is just studying the effect of relative permeability, and you see basically there's almost no effect on this from the shape. Now all of these have similar or the same critical saturations, I think. But basically you see there's no effect on the CGR variation from the rel perm curve itself. These are increasing and decreasing rates, just showing here. So increasing rate.
Sensitive. Oh, sorry. How sensitive is CGR on critical saturation?
I don't think it's at all sensitive to critical. I don't know if we show it here, but the time it takes to reach the flat would change somewhat with the critical oil saturation. But I don't think the actual value would change at all. That's a speculation. I have to do the calculations to see that. I'm not sure why we didn't study the endpoints are equal. So maybe later in the presentation it's done, but I don't think it affects the relationship here, but the time it takes to reach it, maybe. I'm not sure.
Okay.
Here on increasing, decreasing rate, basically you see you get a much faster stabilized GOR if it's increasing rate. The problem with the decreasing rate is that when you decrease the rate, that stabilized oil saturation is going to decrease, and it takes a lot longer to decrease to a new stabilization than it does to increase. Because with the increase, it's just you're condensing out every minute a certain number of drops of liquid, and it's just building up. Okay, but when you have to remove it, it has to be stripped away, so it just takes a lot longer, and you get this clear transient effect shown in red here. Yeah, and this is the the amount in the well stream of the C30 plus, the very heavy component. Correct number up here is shown here. And for the decreasing rate, you see it's never even close. It's not really close for as you get to higher and higher rates here. The change in saturation pressure, increasing, decreasing rates. Not sure what it is. Anyway, there's quite a bit of discussion on this in that presentation, and then the final slide from this is from this SB paper 28-829. That's the paper that also deals with isokinetic. This is SPE 28-829, deals with this isokinetic, and as well it is the same paper that introduces this ECM method. So this paper is kind of a go-to paper for sampling gas condensates. And then this presentation was never made into a paper. It's just the presentation, but that's so the sampling for the two purposes of just getting PVT data of not contaminated samples for EOS building. And the second is this mapping reservoir composition or initial solution gas oil ratio spatially. Okay. This can be used for both. Let's call this A and B. Can be used for both A and B, but on the B, you may have to back out the producing CGR variation with rate, something like we just looked at now, to get an estimate of the in situ. If it's near saturated, then it may be difficult to get. Sometimes we can use it for initialization, but not always, certainly always for building here. Open hole formation testing can be used always for B. And sometimes for if the samples are not heavily contaminated with oil-based mud. There'll always be some oil-based mud contamination if you're drilling with oil-based mud, but if it's low enough, you can, or if you don't have the separator samples, you may have to use contaminated samples to build the equation stain model. And equilibrium contact mixing, which I'll explain here second, can be used for both A and B. And it's really ideal for both of them. So if you have a saturated gas condensate with associated equilibrium oil, saturated system, then the ECM method is really something you should consider seriously using. That also eliminates the need for the isokinetic sampling correction. Now, on this footnote, I'm not going to go into great detail here, but in this second footnote here on open hole formation testing with oil-based mud, okay, there's a report and a presentation. These are not published, but they're open. Work that we did over about a 2-year period. Bob Mott was working with us to do this study, and that information is given again in the references, I think. The papers should be here somewhere, I hope. This one here. Oil-based mud contamination in open hole gas condensate sample. So everything you would ever want to dream about knowing about this particular issue, how to decontaminate, whether you can decontaminate to what level of accuracy, if you draw below the dew point and you have contamination, on and on and on. We tried to answer all of the questions in our that we could come up with. And none of this is published by anyone in the industry, so it's a good go-to paper. It was all done with detailed simulation of an MDT tool with a fully detailed compositional EUS model. I think all of the model data sets there is all run with sensor. Those data sets I think are available publicly if you want to actually look at it for your own sake. You could convert them easily, I think, to Eclipse 300 probably. So that together with the presentation, I think that's probably, yeah. So bottom line is that the composition collected, regardless of the degree of contamination, can be mathematically decontaminated to yield a very good estimate of the in situ fluid composition. Almost always, and with a high degree of accuracy. That's bottom line, the important result from the study. Okay? And consequently, this is really, in all cases, that's why I said this is always good for getting compositions for mapping, because you have an exact X, Y, Z coordinate for mapping and an exact or very near exact in situ composition. You might convert that composition to a CGR through a multi-stage separator process, or this simple correction using the COG and the C5 plus, mole percent, C6 plus. But, basically it's very reliable for the mapping part. Any questions about about sampling. I'm going to get to the equilibrium contact mixing real quick. There was a question there, I think, Bartek.
Is it possible to somehow physically decontaminate a contaminated fluid sample?
Only if you're the woman up above or the man up above, and I don't think we're going to get there. So.
No.
But what you can say is that if you're interested in some property of the mixture of the sample that's contaminated, like I've got a measured dew point, I've got 6% contamination level, I've got a dew point. How do we think that the dew point varies with the level of contamination? So what you can do, you don't go towards the 0 contamination, but you go from 6 to 10 to 15 to 20. In other words, you tell the lab to create 3 new contaminated samples, starting with the first one, and then you map dew point, or whatever property you want to look at, versus level of contamination, and back extrapolate to 0. That you can do. But we would only do it if we can't get or don't have separator samples that we can measure PVT properties on. Because there you're trying to figure out what's the dew point of an uncontaminated composition, of an uncontaminated, basically. The composition of uncontaminated we can mathematically find, but what its dew point is, we don't know. But we could do this kind of experimentation where you add amounts of, and try to determine it that way. What you'll normally find is that the dew point doesn't vary much with oil-based mud contamination. I think there's a paper on that by Tor Austad. Pretty sure of that. I think you can get some lab data, percent oil-based mud contamination. I think on the SB there's a paper by Tor Austad and maybe some other people where they look at some of the property variations with oil-based mud contamination level. Okay. So then we're to the last topic of this equilibrium contact mixing. So we're talking about any kind of reservoir that has gas cap, oil, where we have saturated GOC. So you've got, basically pressure depth data. Looks like this. Gas gradient, oil gradient. Okay. And so the idea is that there's really 2 types of this procedure. So in the one case, we just call that we've got we have a gas cap sample, but maybe the bottom hole flowing pressure is much below initial reservoir pressure, so we suspect the wrong CGR. Okay, and then B, we've got an oil sample, any type, bottom hole sample or maybe a separator sample, doesn't really matter, and right or wrong, typically you'll get a pretty reasonable GOR during testing of oil. Okay, so maybe we've got the oil sample is taken down here, and the gas sample is taken here. Okay, so what this ECM procedure does it just says mix, equilibrium contact mixing. It says mix A and B in a PVT cell. And there's a rule of thumb basically that the oil volume percent oil volume, greater than about 30, it doesn't matter. 30 to, whatever you want, 70, 80%. Okay. But the idea is that you want to have enough sample of, when this is equilibrated, you just equilibrate this at the pressure at the GOC and reservoir temperature. And we usually recommend overnight, just a 24-hour. It's mixing, it's rocking, it's equilibrating this two-phase system. And then you basically remove the equilibrium gas, and we say that this is essentially equal to the GOC gas. And you do your typical CCE of that sample, CVD, and then we remove the equilibrium oil. Basically say that's equal to our GOC oil, and then again do a CCE and a DLE viscosity separator test. I'm not going to write it identical to, but I'm going to say very close to, equal. And the level of accuracy is like .01 to 0.1 mole percent on all. Well, it's actually better than that. It's basically should be 3 significant digits, I think is what we found. Significant digits on every component. So maybe the methane composition exactly 72.036 from the the model, the actual is at the gas oil contact. So this is exact, and this ECM would typically be 72 point, maybe 0.8 to something like that. So that's basically a very simple way to create samples as if we had gone into the reservoir and collected a sample right there in the pores around the gas oil contact. So you mix just the samples you have together in a PVT cell, have, maybe 50% oil volume, 50% gas volume, that's a good rule. Equilibrate it overnight, take out the equilibrium gas. Of course, you measure the composition of this gas, composition of the oil. You get the composition, CCE, CVD, CCE, CVD. So that's your complete set of laboratory tests. And it doesn't matter whether the gas cap got the wrong CGR, the oils the wrong GOR, because what happens when they equilibrate, any components that were missing from the gas cap sample, particularly the heaviest components, are given by the oil when it equilibrates. And there's such small amounts that need to be moved over to the gas that it doesn't really affect the oil composition at all. So it's, and likewise on the methane, the methane equilibrates. So that's the first ECM method. The second ECM method is what we call ECM from a gas coning oil well. Okay, so you basically have your gas oil contact, you've completed the well here, and sometime during the testing we get this coning in. Typically you'll see it on the producing GOR versus time, you know, maybe the initial rate, and then you go to a new rate. Basically you start seeing this going up like that. And then it's not uncommon, but most people say, oh shit, why did we take a sample here? But the ideal situation is to take a sample here after you get the coning of the gas into the well. And it's very simple. You just simply take that coning sample, take that sample, and you just follow the same procedure starting here. So just mix the coning sample. Will typically be separator samples. Recombined at the GOR of the test, which is coning. It's obviously greater than the initial solution gas oil ratio, which is here. And just go through the equilibration. Get the GOC oil, gas first. And what we actually show here is that the composition of this ECM is within probably 4 to 6 significant digits, the same as the actual GOC composition. It's even better than doing the other. So the only thing here is you don't really have that much control over how much equilibrium gas and how much equilibrium oil you get, right? Because it's coning. So we actually tell you, we have a design gas oil ratio equation in the paper that says if you go to that GOR, you'll get greater than 30% oil or something like that, or you stay within it. There's a kind of a design sampling, but normally it's okay because you basically want to have enough gas that you'll have a gas volume that's big enough to do a CVD and CCE test on. So that's the sampling for with the ECM method. 2 types. Any questions? Again, this same paper discusses this in detail. One question to the participants from Qatar Gas Group. do you know of any, whether they've actually found and sampled an equilibrium oil initially? Because I know it's very near saturated. I've just never heard or seen of oil samples being found or collected from the North Field. If you can say, maybe it's confidential.
Actually, if I can weigh in, we only get gas sample. We are not really into the oil sample process and otherwise we mainly deals with gas sample.
Okay.
There are another companies in the field, other petrol who are really related to these kind of samples.
Okay, so have you heard of anybody actually finding when they did MDT sampling, they actually sampled oil?
Actually, my experience is limited, but
Okay.
not. I never heard of it.
No. Okay. Okay. Yeah, so I think that's pretty much everything on sampling that I wanted to talk about. The isokinetic, it's seldom used anymore. It's probably seldom needed. Like I said, if it's a leaner condensate with very high rates, then you might justify using it. So it's discussed in great detail in that same paper. So I think that I'll just leave that to you to read. Okay.